All right. So I'm here to do number 10 this time. So I jumped all the way down to one of the hard ones at the end. In this one, I've given you the image height and the object height and not given you any of the distances. And I've given you the focal being positive 10 units again. So it's a converging lens. And giving you the image height and the object height is just sort of a tricky way to give you the magnification. So the first thing we're going to do is look at the equation where magnification is equal to the negative di over do, or negative si over so. But that's also equal to hi over ho. And so when we divide 4 divided by 2 units, we see that the magnification is 2, which means that the image is going to be twice as big. Since it's positive 2, it's going to be upright. And so we already have a good sense that this is going to be one of the virtual cases when the object is inside the focal length. So that's what we're expecting to see, but we got to crank out some math here. We have the focal length is 10 units, and so we really have kind of a hard situation because when we look at 1 over f equals 1 over si plus 1 over so, we only have one of the 3 numbers here at this point. So we need more information. Luckily, since we know that negative si over so, which is the magnification, is 2, I can make a little equation and do a little substitution. So let's see how that works. I'm first just going to solve for si. So I multiply both sides by so, and I take the negative over. So now I have that si is negative 2so. So now in the thin lens equation here, where si is, I'm going to substitute in negative 2so. So negative 2so goes plopped right in here where si was. I also put in where f is. I put in a 10. And this is 1 over so. We're leaving 1 over so for a moment. So now I have a fraction here, and in order to add them, I'm going to need a common denominator. So what I'm going to do is I'm going to multiply this one by negative 1 on the top and the bottom. And I'm going to multiply this one by 2 on the top and the bottom. So I still have equivalent fractions, but now they have common denominators. So this becomes negative 1 over 2so, and this one becomes 2 over 2so. And now that I have a common denominator, I can add them. And obviously 2 plus negative 1 gives me a 1. The left I just left alone, 1 over 10 the whole time. At this point I can cross multiply and solve for SO, and you'll see that SO equals 5. Okay, and that makes sense. We expected the candle to be inside the focal length. And remember the focal length was 10, and sure enough we're at 5, so we do have the virtual case that we expected. We can get SI because remember we had this original magnification that we knew. Since SI is negative 2SO, we now know that SI is negative 10 units, which is exactly what we expect because SI needs to be virtual, which means it needs to be negative. And you'll notice we could plug back into this original, the numbers we have now with SI and SO, and make sure that we get 10 for F if you want to spend that extra time and just check your work. But I'm going to go ahead and do the pictures here instead. So moving on to this picture, we know that the lens is converging. We know that the object was placed at 5, and we expect the image to be on the wrong side, not over here where we expected it to be converging, but instead over here on the left. Since the object is inside the focal length, the lens, even though it's a converging lens, fails to completely converge the rays. The rays were diverging, they're still diverging, even though it's a converging lens. And that's because the object was just too close to the lens. Okay, so how do we do this? Well, the ray that was coming from the focal length now turns and is parallel. The ray that goes through the middle, that's the same as always. We like that one. And then this one, the one that was parallel, turns and goes through the focal. And now what we're going to do is we're going to say these three rays appear as if they were coming from somewhere. Okay, so they're going this way, but they look like they came from way back here. Okay, this one looks like it came from way back here. Similarly, this one looks as if it came from way back here. And so this reverse ray tracing brings us back to our image location, which sure enough is over here at negative 10. With the mirror, we have a similar case. The parallel one gets reflected through the focal. Okay, the one that's as if it was coming from a focal gets reflected parallel. And finally, the one that hits the middle of the mirror reflects at the same angle. And if we reverse ray trace this one back, here's my virtual image. Reverse ray trace this one back, there's my virtual image. And so sure enough, we get exactly the correct situation because we have a focal length that's bigger than our object distance. Okay? And so the image is over here on the side we would not expect it to be on. That's how you do number 10. And good luck. I might get to another one. I'm not sure. There you go.